Good afternoon, fellow scholars. It is I, once again, Chris Crowe, here to bring you another Math for Teachers lesson. This time it's on chapters 2 and 3, going over the different topics of union, intersects, and different computations dealing with different numeral systems. So without further ado, let us get into the action. So what you see here is obviously the beginning of the lesson. And moving on to our first problem, we're going to be using a standard Venn diagram. Now, Venn diagrams are typically used to compare and contrast different things, whether they be numbers or characteristics of different things if you're in a different type of class like literacy. And so, moving on to the actual problem, we see that these different Venn diagram circles have been labeled A, B, and C respectively. And now we see this little equation looking thing right here. We see U equals A, B, C, D, E, F, G, H. Now the U is not actually a U per se, it's what's known as a union sign, and I'll explain what union is in just a moment. So going forward, we can see that each of these Venn diagram circles have been given a different set of letters. A has B, C, D, G, H, B has D, F, and H, C has D, G, and H. Now I want you to pay close attention to the similarities and differences between those three sets of letters, or items as sometimes people like to call them, because they tie into the goal of this Venn diagram. So moving forward, we're going to place the different letters from the sets into the actual Venn diagram. As you can see, B was just placed in A, and if you notice, circle A is the only one of all of these Venn diagrams that has the letter B. So it shows up in letter A, or Venn diagram circle A. Moving forward, we're going to place all of these letters in their respective Venn diagrams, some of which are shared by more than just the one diagram. Some are shared by two of them, and some are shared by all of them. All of them, being the case D and H, are shared by all three of them. G is shared by A and C. F is B only. And then A and E, you can see, don't exist inside any of the sets, so they're outliers. They're outside of the Venn diagram, so we don't have to pay attention to them just yet. Now we'll get rid of the sets, and moving forward, we've got the same Venn diagram as before. So now what we need to figure out are the different set equations. So right here, we've got all of our questions, our problems right in front of us. So we'll start with the top, B union C. Now, if you don't know what union means, union is basically saying it's an OR. It's an OR statement. So B union C is referring to all of the letters or items inside B or C. So if we take a look at Venn diagram circles B and C, we see that B contains F. We see that C contains nothing on its own. And we also see the in-betweens, D and H. Now C does contain G, but it's also coupled with A. So when talking about union, you're going to want the ones that are either in B or C. So in this case, it's D, F, G, H. Now it can be in both, but it has to be in one or the other. Now the second one we see is A intersect B, the upside down looking U symbol. Now intersect is a both statement. It's kind of a contrast to the union sign. So when something says intersect, it is specifically talking about the items in between the two Venn diagram circles, or in both of them at once. So in this case, A intersecting B means that we have to pick apart the items that are in both Venn diagram A and B, and that is our answer. Now we can see G is not one of them because while it's intersecting A, it's part of C and it's not part of Venn diagram B, so that's not going to be one of our answers. We can see that B, C, and F are in either A or B, but they're not in both at the same time. A and E are still outliers, we're not paying attention to them, so our only possible solutions are D and H. If you're paying close attention, you'll notice that both D and H are inside Venn diagrams A and B. They're inside C as well, but that's inconsequential to the answer. Moving to the third one, we see B intersecting C. Now, just like with A intersect B, we have to pay attention to the items that are within both B and C at the same time. Once again, we are given the answers D and H because, as I said before, they are in both B and C at the same time. And now to the fourth one, we see A union C. Now, if you remember what I said about union, it's an or statement, or an and sometimes if you want to consider. So A union C, that's A items and C items. So everything within A and C. So we see B, C, G, D, and H are all within A and C. So B, C, D, G, and H is going to be our answer for that set. Now the fifth set we see is just A, but A has a line over it. That's not something we've encountered yet, and I'll explain what that means. The line over A is telling us that every item that is not within Venn diagram A is going to be the answer to this. Okay, so whenever you see that line, it means that whatever that line is over is not going to be part of the answer. So we are getting rid of every item that is part of a Venn diagram A. In this case, it's B, C, G, D, and H because they're all part of A in some way. So the answers here are going to be A, E, and F because items A and E are outside of the Venn diagram completely, which means they're not part of A. And F is the only other item that is not part of Venn diagram A in any way. It's exclusive to B only. Now, the sixth set is A intersect C. Now remember what I said about intersect. It is everything in both Venn diagrams A and C at the same time. So, like the other intersects, we're going to take a look at the Venn diagram. We can see that G, D, and H are all within A as well as C. B and C are in A, but they are A only. F is not a problem because it's a B exclusive item. So our answer is going to be D, G, and H. Now our final set it's trying to be a bit tricky. It's trying to scare you with how much larger it is than the others, but don't get scared. It's just as simple as the others. Now, in this particular one, what you might want to do is follow the rule of PEMDAS, or please excuse my dear Aunt Sally. Now, the rule of PEMDAS is simply stating what you will do first when dealing with equations and expressions and other type of mathematical formulas. So PEMDAS goes parentheses, exponents, multiplication, division, addition, and finally subtraction, PEMDAS. So here we see A unioned to B intersecting C. Now B intersects C is within a set of parentheses, so we'll tackle that first. So B intersecting C, we've seen before, is D and H from the third set above. And now that we have our B intersect C, all we have to do is union that previous answer with whatever is in A. So in this case, B, C are in A, so we will union those with our DH answer. And we are given B, C, D, G, H as our final answer for question 1. Now, the rest of these questions are very similar in certain ways, especially number 2. Here we have our one large Venn diagram circle, and now we're going to see a bunch of different colored shapes popping up. We see some hexagons, we see some circles, we see some triangles down below, and we're going to see some triangles to the right, as well as more circles. Now, if you notice, certain colors of certain shapes are not within the Venn diagram. I'll explain what's going on in a second. We see our union sign at the top, and we see that this Venn diagram we call A. The formula for this one is S intersecting, not T. What does that mean? Well, we're going to let letters, or variables if you want to call them, explain or stand for the different items you see on screen. So in this case, S is going to represent small, and T is going to represent triangle, as you can see down below the Venn diagram, as well as the different small sizes of the shapes you see. So now the formula is saying S intersecting, not T. Now if you were paying attention to the previous question, you understand what intersect means. So if we're going to make this simpler, it's asking you to understand that within Venn diagram circle A, we have small intersecting everything that is not a triangle, T. So every item you see that is not a triangle, and that it also is not large, so it would be L, is going to be within the circle. So every small non-triangular shape. And we see in the Venn diagram, we have two hexagons, different colored, and we have two circles, different colored. Now, using this, we're going to move on to the actual part of the question. We see all these different sets popping up. Well, you now have an answer at the very least, but with these 4 different sets, we are going to look at the Venn diagram and pick apart what goes where. So for this first set, we see L intersecting H. Now, L is going to represent our large shapes, and then H is going to represent our hexagons. And since it's intersect, that means the two item letters are going to combine in a way. So we have large hexagon shapes. So we see here our large hexagons, blue and red for diversity. Our second set is C union H. Now C is going to represent our circular shapes, so the circles you saw on the Venn diagram. And then the H obviously is going to represent our hexagon. So we have C unioned to H, and union is going to be the OR statement. So in this case, we're going to have circular unioned to hexagon. And as you see here, that's our answer. We have all of our circles unioned with our hexagons. They're not combined in any way, so it's circle or hexagons. Our third set, we have not T intersecting R. Now if you remember, T is going to represent our triangle shapes, but it has the line above, which I stated before is not. So we have not triangles intersecting R. R is representing the color red in this case. So we have every shape that is not a triangle intersecting with red. So that's going to give us all of the other shapes red that are not triangles. So our red hexagons and our red circles. And now for our final set, we have C intersecting S intersecting R. Now if you notice, there's no parentheses to separate them. Don't let that scare you though. While we can't exactly apply the rule of PEMDAS, we can, however, go from left to right like we normally would. So starting with C, we see it intersects S, and then the S is intersecting R. If you want to place a pair of parentheses, you can do that if it helps you in any way. We can place them around, let's say, the C intersecting S first. So we have C intersect S, so that's circle intersecting small. Now that we have a small circle to go off of, small circle will intersect R. So our answer, if you're paying attention, is going to be a small circle, or small red circular shape. Not that difficult. can be a bit jarring at times if you're not paying close attention or if you're not taking good notes, but when broken down, union and intersect are incredibly simple operations that you can use to do most kinds of separating, almost like a tree diagram. Now, moving on to our next question, we're going to talk about numeral systems. So right here, I've brought up a picture of the Egyptian numeral system. You can see there are several different types of shapes, some of which are kind of funny looking. Now, we are going to use this graph, this Egyptian numeral system graph, and we're going to figure out what this long equation at the very bottom is. Now, it's okay to be kind of nervous when you're dealing with something that represents a number but is not actually. You can try to think of these symbols as variables, the different letters that we use to often represent numbers and to use in advanced different forms of algebra. So here we see three pointing finger symbols. We see 5 what looks like an intersect symbol, although according to the graph it's called a heel bone, but we'll stick with upside down U. So we see after that 4 dashes, they look like eyes. And all of that combined is going to equal a number in what we know as the Indo-Arabic numeral system. Our 1s, our 10s, our 2s, our 3s, our 5s, our 20s, our standard number system. So here, we need to break down what these different symbols represent as far as numbers go, the Indo-Arabic system we use. So, moving forward, we can see I've set up these different symbols to equal their numbers separately so that we can add them together and get our actual answer. Now, if you're looking at the graph, you can see that the pointing finger symbol represents the number 10,000. So one of those symbols is going to represent our number 10,000. Now adding those together, we have 3 of them, so our number is going to be 30,000. Moving on to our second set, we have the 5 union or intersect symbols, the upside down U's. And if we're looking at the graph, we can see that one of those, the heel bone symbol, represents the number 10. And since we have 5 of them, we can infer that 5 of them is going to equal the number 50. And now we move to our third set, which is the 4 vertical slashes. And if you remember from my first lesson way back when, vertical is up and down, just in case you're confused. Going up and down, horizontal is side to side. Now, if you look at the graph once more, you can see that the staff symbol, the eye-looking symbol, represents 1. So the individual 1 is represented by 1 staff. And if we have 4 staffs, then that is going to equal the number 4. Now, combining all of these numbers together into the symbol equation we see down below, our final set, we can combine the numbers to give us 30,054. Not too difficult. Now we'll move on to another numeral system, no longer the Egyptians, but rather the Roman numeral system. Not using the same crazy looking symbols that the Egyptians do, but rather a set of letters, what we would call or know as variables. Now here we can see this graph is IVX LCD with M at the finale, representing the numbers 1, 5, 10, 50, 100, 500, and 1000 respectively. So now, with this graph in mind, we have to find out the system below, the set of MCM XXX V2, or rather II. Now, using the graph, we're going to pick apart all of these different symbols to find out what their place values are, what the numbers they represent are. Starting with M, we can see that it's 1,000. Now I've got CM down below. Now you might be wondering, why do you have them grouped together rather than apart? Well, that's because the Roman numeral system can be a bit tricky sometimes. But I'll explain that in a second. So if you're thinking that CM is going to simply combine C and M to create 1,100, which would make the total number over 2,000, you would not be wrong to think so, but you would still be wrong. CM does not actually represent the number 1,100. The reason being is when certain symbols are combined in a specific combination, such as CM, the actual number it represents is going to be the right side symbol subtracted with the left side symbol. So in this case, rather than being 1,100, it will be 1,000 minus 100. So CM actually represents the number 900. That can be kind of confusing, but if you remember that rule, you should be good to go whenever you are dealing with a multiple variable symbol. Now moving on to the final three, we see X is worth 10, V represents 5, and the I is the 1. Now if we combine all of these numbers together with simple addition, we get 1,937. And the reason being is because of the amount of symbols we have. So MCM is the 1,900. The three X's are 10s, so they're going to be 30. The V is 5, and the two I's are 2 combined, 1,937. Moving on to our third numeral system, we leave the Romans for the Babylonians. Now here we see this remarkably somewhat confusing number system. We see 4 sideways arrows combined with a final downward, obtuse-looking triangle. Now, the Babylonian system is simple but also somewhat complex. It has different place values, but for this moment, this particular question, we only need to look at what these arrows represent, and as well as the one place value we're going to be dealing with. So looking at the symbols, we can see 1, 2, 3, 4 sideways triangles is going to represent 4. And then the final obtuse upside down triangle represents 10. Moving forward, we can see the number 41 times 1. Now that's because we're going to multiply the numbers 10 and 1. No, sorry. The numbers 4 and 10 to get 40. And with the 1 place value we're dealing with, which is all of the symbols together, is going to represent 1. And so with that 1, we will put it together to create 41. And then we're going to multiply that number, 41, times the place value, which is represented by 1. So 41 times 1 is going to equal 41, which is what those arrows will represent. And now finally, we move on to the Mayan numeral system represented by this graph here. Very different looking, even compared to the Babylonians and the Egyptian symbols. Now here, we're going to see the different place values with which the Mayans dealt with. Now there's only 4 of them, as you can see. Descending in amount, we see 72,000, 360, 20, and finally the number 1. Now with those 4 place values, we're going to separate these different numbers. As you can see here, this at the very bottom left corner is the symbol we are trying to identify. We have a lone slash at the very top. Our second item is a dot with a slash below. Our third item are 3 dots combined. And our final item are 2 dots over 3 slashes. Now if you're paying attention to the graph, you can see the lone slash represents the number 5. So 5, being the first number we're going to see, is going to be multiplied by the first place value number, in this case 7,200 or 7,200, whichever you prefer. The second item, the dot and slash, is going to represent the number 6. And so 6 will be multiplied by the second place value number, 360. The 3 dots in the third item represent the number 3. And since we are following the pattern, 3 will be multiplied by the third place value number, 20. And finally, the 2 dot 3 slash item is going to represent the number 17. So 17 will be multiplied by the final place value number of 1. So we have 5 times 7200 plus 6 times 360 plus 3 times 20 plus 17 times 1, which will give us our grand answer total of 38,237. All very interesting and difficult numeral systems in their own ways, but all of them having tricks that will allow you to complete them in their entirety, translated into our Indo-Arabic system. Speaking of helpful methods, our next question is completely centered around one, which was my personal favorite to use while growing up. It's called the lattice method. Now here we're going to have our two numeral sets, that'd be 28 and 32. Now the way this method works, it's the lattice method, also known as the box method for a simpler name, is you place the numbers along the two sides of the square, or the box. You will draw lines in between these numbers to separate them into their own distinct boxes, and then use separate lines to make sure all of them have their own individual spaces. And so what we're going to do next is we're going to multiply the single numbers along the boxes. So we're going to start with 8 times 3, which will give us 24. So we'll put down 24 in the individual boxes, the 2 in the top, the 4 in the bottom. We'll do the same thing with 3 times 2 equaling 6. Now when you get a single digit answer like 6, what you'll do for the second space, or the first space rather, is simply put a 0 above it, representing its single digit nature. And now that we've gotten our top row, we'll move down to the bottom row. Once again, we will multiply 8 by 2 this time, which will give us 16, putting the different numbers in their respective slots. And finally, 2 times 2 will give us 4. And so now the final step of the lattice method is to add all of the numbers together along their same slots until we get our final answer. And what I mean by that is you can take your hand and cover up all of the current rows that you're not dealing with. So in this case, we'll cover up all of the other numbers and we'll focus only on 6. So we have 6 alone by itself, so 6 is our first number. Moving upwards, we see that 4, 1, and 4 are in the same row together. And so they are going to be added together. So 4 plus 1 plus 4 is going to give us 9, which is our second number. Our third row is going to contain the numbers 0, 6, and 2. As I said before, simple addition will add 6 plus 2 together to give us 8. The 0 is obviously a 0. And finally, 0 is in the fourth row, and since 0 is 0, we're not going to pay attention to it. So the final answer of 28 times 32 is 896. Now let's move on to a couple other lattice method examples with a different graph for the sake of putting everything together. So here we see the numbers 273 times 628. Now like I said in the previous questions, don't let the big number scare you. It's only an increased number value. The sum is the only thing that's really going to change. It's going to be a bigger answer to bigger numbers. So, as I've said before, we're going to separate all the different columns with lines. So, moving forward, we're going to multiply 3 by 6, which is going to give us 18. Next, we'll do 7 times 6, which is 42. And finally, we will do 2 times 6, which is 12. Moving down the row, we now have 3 times 2 equaling 6. we have 7 times 2 equaling 14, and we have 2 times 2 equaling 4. On to the final row, we have 3 times 8 equaling 24. We have 7 times 8 equals 56, and we have 2 times 8 equaling 16. And, like I said previously, we're going to cover up all the numbers we're not working with and slowly add all the ones in the same rows until we get our final answer. So our first number is going to be 4 because it's by itself. The second is going to be 6 plus 2, which is going to equal 14. Now, if you notice, I'm not putting 14 all as one number. That's because they can't have more than one number. That's not how the lattice method works. So what we're going to do is we're going to keep the 4 in the row, and we'll bring the 1 to the row following. So we see 6 plus 5 plus 4 plus 0 plus 8. And all of that combined with the 1 from 14 is going to give us another 14. And moving on, again, 1 plus 4 plus 1 plus 2 plus 1 plus the previous number's remainder, we'll call it. We get 1. And following that same pattern, we get 7. And finally, 1. So our final answer, 273 times 628, is going to give us 171,444. Moving on to another lattice method example, we see 964 times 593. Once again, we're going to draw lines to separate the rows, and we will move along the different numbers until we have everything we need to complete our addition. 4 times 5 is going to be 20. 6 times 5 is going to be 30. 9 times 5 is going to be 45. 4 times 9 is going to be 36. 6 times 9 is going to be 54. And 9 times 9 is going to be 81. Our final row will be 4 times 3 equaling 12. 6 times 3 equaling 18, and 9 times 3 equaling 27. Once again, we will move through these different numbers, adding them together and carrying our remainders into the following row. We're left with 2, 5, 6, 1, 7, and 5. With our grand total of 964 times 652 being 571,652. Now, on to our final lattice method question. We see 4,952 times 243. So now one of the numbers has grown even larger. But as I said, so long as you don't let it scare you, you will complete this problem with little to no effort on your side. The lattice method is an incredibly easy method to use, although time-consuming, so don't let the entire operation slow you down. If you've completed one, then you can use your deductive reasoning skills to move forward in how the patterns may work. So once again, using deductive reasoning, we're going to blow through some of these. 2 times 2 is 4. 5 times 2 is 10. 9 times 2 is 18. 4 times 2 is 8. 2 times 4 is 8. 5 times 4 is 20. 9 times 4 is 36. 4 times 4 is 16. 2 times 3 is 6. 5 times 3 is 15. 9 times 3 is 27. And 4 times 3 is 12. Once again, we're going to cover up the numbers that we're not paying attention to, and we're going to add all the numbers within their respective rows, carrying the remainders to the next row over until we reach our final one. So 6 alone is going to be 6, 5 and 8 is going to be 13. Carrying the 1 over to the next row, 7 plus 1 plus 0 plus 0 plus 4 plus the 1 is going to give us another bout of 13. So once again, we're going to carry our remainder over. We're going to have 3 as our first number, carrying over the remainders. We're going to have 0, 2, and finally 1. Now, if you've carried over your remainders correctly, if you've added correctly, if you've put everything together, your final answer for 4,952 multiplied by 243 is going to be 1,203,336. All of this can be solved using the lattice method, deductive reasoning, your critical thinking skills, as well as whatever minor tricks you might need to help along the way. Now, moving on to our next questions, we're going to be dealing with whole numbers, but with a twist. So here we see 883 plus 465 all over 134. Now, the purpose of this question is we're going to be dealing with rounding left, rounding to our left decimal number. So what does that mean? Well, I'll show you. So here we see the number 883. Now, rounding left, we're going to pay attention to our middle number, the 8, in between 8 and 3. So here, rounding left means if you're dealing with a number that is 5 or larger, then the number you're rounding to is going to increase by 1. And then every number after that is going to turn into a 0. So in this case, we have 883. Now the 8, the middle number we're paying attention to, is a larger number than 5. It's 5 or larger. So the 8 at the very beginning of the number will change to a 9. And then every number after that will turn into a 0. So after rounding 883 to the left, we're left with 900. Moving on to the next, we see 465. Once again, we're going to pay attention to the middle number. 6 is, in fact, a number that is higher than 5. And so, following the same logic, 4 will change to a 5, and every number afterwards will switch over to a 0, leaving us with 500. And finally, 134. Now, if you're paying attention, you'll see that 3 is the middle number, and 3 is not higher than 5. So what do we do when we encounter a number that's not 5 or larger? Well, similarly, the same rule, only rather than increasing the number to the left, we're going to leave it alone, but every number after that will still become a 0. So since 3 is not higher than 5, 1 will remain as it is, but the 3 and 4 will become zeros, leaving us with the number of 100. And now, taking all of these numbers, we're going to replace the old numbers with the new ones in the expression. So now we have 900 plus 500 over 100, which gives us our grand total of 14. Now let's move on to our second example. We have 5 times 254 plus 523 over 35 plus 7. Now they've gone and done us a loop. They've gone and done us real funny like, but we're not going to let them scare us. No, we're going to keep moving forward. So, for all intents and purposes, we're going to leave 5 alone. It doesn't need to be rounded. It only has the one digit. It can't be rounded. So, first we're going to add the denominator numbers together. Denominator is simply the numbers below the division line. So in this case, 35 plus 7. So 35 plus 7 is 42. And now that we have our denominator number, we can move on to our top numbers. And we're going to repeat the same method that we did before. Paying attention to the middle number, rounding to the left number, we see that 254, 5 is 5 or larger, and so the 2 will increase to a 3, and every number after that will turn to a 0. With 523, we see that 2 is not a number higher than 5, so 5 will remain as is, and every number will switch over to a 0, giving us 500. And now we're going to take a look at 42. While it's not as big as the others, it is still more than one digit, so we have to pay attention to it. So we see 42. Now 2 is not a higher number than 5. So what are we left to do? Well, the same thing we've been doing. We're going to I apologize. Let me get back to where I was. Alright. There we go. I apologize for that. Now, going back to where we were, we can see that 2 is not a number larger than 5. So what are we to do? The same thing we've been doing. We're going to leave 4 as is, and every number afterwards will be replaced by a 0. So we're left with 40. And now that we've got our new expression, 5 times 300 plus 500 over 40, we can be left with our grand total of 50. Now we're going to move on to our final example, 620 times 430 over 293. Again, we're going to repeat our same cycle as so far. We're going to pay attention to the middle number. It is not larger than 5, nor is it 5. It's a 2. So the 6 will be left as is, and all numbers afterwards will be replaced with a 0. 430, the 3 is not larger than a 5. So the 4 remains as is. The 3 and 0 will turn to zeros, creating the number 400. The 293, we can see that 9 is a number larger than 5. So the 2 will increase to a 3. The 9 and 3 after will be replaced with zeros, leaving us with the number 300. All of this creating our new expression 600, times 400 over 300 will give us our grand total of 800. Now, rounding is all well and good, but there are different number notations that will throw you for a loop no matter what kind of mathematical equation you're dealing with. Multiplication, subtraction. There are other notations that can be just as, if not more difficult, if not paid attention to properly. Here, we see a rather interesting looking problem. We see 432 5 plus 133 5. Now what does that mean? Well, the 5 represents base notation. So similar to a number system, but not a completely different societal one. This is simply counting in a different notation. So when you think of our counting system, what we call base 10 or decimal system, we think of the tens, the 10, 20, 30, 40, 50, or rather the ones, tens, hundreds, thousands places. Now with a different base number notation, those places are going to be replaced with something different. So base 5 notation, you're going to have our 1, and then you're going to have, or rather the 5, as we should say, so a 5's place, and then increasing up to a 25's place, because 5 times 5 is 25. Same way 10 times 10 is 100. And then so on and so forth, increasing in the different places. So instead of 10s, we have 5s. So here we have to add these numbers together in a different base notation, which is not something we're used to. But luckily, we have a method to exact our answer. So here I've set up 432, but separated. The way you solve base notation addition is you break apart the numbers, and then you multiply the individual numbers by the 5's notations. So in this case, 4 is going to be multiplied by 25. 3 is going to be multiplied by 5. And 2 is going to be multiplied by 1. 1 is going to be a constant in all base notation sets. And then we're going to do, once we have our answer, which is 117, we're going to do the same thing with 133. So 1 times 25 plus 3 times 5 plus 3 times 1 equals 43, which gives us our grand total of 160. You're going to add the answers together, and the sum will be the answer you're looking for. And if you want to be able to check that answer, you can simply break apart the answer, the sum number, and do the same trick that we just did for 432 and 133. And if you get the correct answer, then you're on a roll. Now, slashing across the screen, we're going to look at our second example. Now this one is base 6 notation. Obviously different from base 5, but the method will remain somewhat the same. So instead of the 5's numbers, instead of 1, 5, and 25, our base notations will go by 6. So rather than 1, 5, 25, we'll have 1, 6, and then 6 times 6 is 36. So that will be our next place number. So looking at the base 6 notation, we see 628 plus 73. Now, the method, as I said, will remain the same. So we're going to break apart the number 628, only instead of the 25 base notation numbers, we'll be doing 36, 6, and 1, which gives us our grand total of 236. And again, we'll do the same thing, breaking apart. There's supposed to be a 4 there, I apologize. But we will break apart the number once more. So 7 times 36 plus 3 times 6 plus 4 times 1 equals 45. And so adding the sum numbers together, we are given 281. Now, one thing you must remember is when you get your answer, you must put down the base notation. Otherwise, the answer could be considered wrong. So whenever you get 160, you have to put 160 base 5. 281, 6 has to be 281 base notation 6. Now, we will move on to our next example. And instead of addition, we're doing subtraction, which is a bit more complicated than addition, but not impossible to do. So here we see 414 minus 43 at base 5 notation. Now, the way subtraction works outside of addition is it has to be put together in the similar way as normal subtraction would, 414 minus 43. So going through, like normal for the moment, we see that 4 minus 3 is 1. Now, obviously, we can't do 1 minus 4, so we're going to have to borrow some value from the 4, which turns it into a 3. And so 3 minus nothing will be 3. So now that we have some value, we can put it into the 1. Now, if you think that you're going to be creating an 11, you wouldn't be wrong, but you would be. You wouldn't be wrong to think so, but you would be wrong to do so. This is where the subtraction differs from our normal method of subtraction. So here, instead of an 11, what you're actually creating is a 5 plus the 1. So the 1 is more or less brought up, and instead of an 11, you are creating a 5. You're separating a group. You're borrowing a 5 from the 4. As how base notation works. So instead of an 11, it's a 5 plus 1, so which equals 6. And then bringing that down, we understand that 6 will subtract from 4 to give us 2, which is our grand total number of 321 base 5. Definitely more difficult than addition, but not impossible once you see an example and you understand where you're going. Once again, I'm going to slash through the screen, and we're going to do 503 minus 24 base 5 notation. Now we're going to follow a similar method as the first one. So we see 503 minus 24. Now if you'll notice, 3 can't subtract from 4 the same way 0 cannot subtract from 2. Now that's going to be a problem. So what we're going to do is we're going to borrow some value from the 5. So the 5 becomes a 4. 4 minus 2 is going to equal, that is supposed to say 2. I apologize. So imagine the 4 as a 2. So 4 minus 2 is 2. No, I apologize again. 4 minus nothing is 4. So now that we've borrowed some value from the 5. We're going to slash out the 0. Now, if you remember, once again, we're not creating a 10. No. That's where this differs from normal subtraction. We're not creating a 10. We're simply creating a 5 plus the 0. So 5 plus 0 is 5. And so 5 minus 2 is going to equal 3. Now, once again, 3 minus 4 does not work. So following the same logic, we're going to destroy the 3. And bringing over the values, we will be left with the number 1. And so 503 base 5 minus 24 base 5 is going to equal 431 base notation 5. And that is a conclusion of our Chapter 2 and Chapter 3 lesson. I apologize for the mistakes. It's been a rough weekend, but I hope that you guys can come away from this learning a bit more than you did about the different computations, unions and intersections, how to better use a Venn diagram, how to deal with different numeral systems, how to deal with decimals and base notations and lattice methods, and all the other good stuff that you're going to learn. Thank you guys so much for listening. I look forward to seeing you again. And once again, fellow scholars, you rock.